Okay, today we're going to talk about conservation properties of finite difference differential equations. So the differential equations themselves that describe our fluid, they have conservation properties, like they may conserve momentum, energy, mass, concentration or total mass of various transported quantities like water vapor, total water, and so on. So there are lots of conservation properties that are important to preserve, and there is no guarantee that our finite difference approximation, and we'll see, as we will see today, that there is no guarantee that our finite difference approximation of our differential equations would have the same properties. You need to actually specially design those approximations to have those properties, conservation properties. So let's start with a simple example of so-called Burger's equation that looks like the following: du dt plus u du dx equals to 0. So this is called Burger's equations, and it's very popular in study of nonlinear instability, and basically this equation, this term is nonlinear. When we studied numerical schemes, we use similar equation, but with u being constant, some constant propagation speed. Here you see that it's itself, velocity is a function of velocity is actually transporting itself with velocity u, and this nonlinear term creates all sort of waves harmonics, shorter waves harmonics that we saw when we talked about nonlinear instability. So this equation tends to produce shocks or very sharp gradients of velocity. So basically, if you initially have some wave that looks like, say, something like that, this is your u, this is x. So as time goes on, you will produce a solution that is very sharp, something like that. Sharp, and eventually it will be shock wave. So that's why it's challenging, because those shortest waves that create this associated with this shock wave, they're not well represented on a finite grid that we have with finite grid stepping. So all the short waves should be earliest to waves that can be represented. As a result, you have all sort of noise generated by numerical. If you have if you're not careful enough, your solution would look something like. So your solution would look something like that. So you have maybe some noise here, and then. So instead of shock, you would have all sort of noisy behavior here. And if you use scheme that does not preserve certain, say, kinetic energy, then this scheme will have tendency to, it has a big, it may generate nonlinear instability, and your solution will blow up. So that's why people kind of use this equation to study various numerical schemes and how they behave, because this term is very common in the models. This is kind of advection of a momentum term, and there are many of those terms in actual equations of motion for atmosphere, for motion of atmosphere or water. So this equation, Burger's equation, is used as a test bed to test certain numerical schemes. So let's consider conservation of momentum. In this case, momentum is just velocity. When we talk about kind of assess, and theoretically the conservation of momentum we will always use periodic domain. So we basically disregard any effect of boundaries or boundary conditions on conservation, because sometimes it's very challenging to conserve certain things in the presence of boundaries, and we may talk about this sometime later. But for now, for simplicity, we just study the numerical scheme, and we completely disregard the question of how boundary conditions affect the conservation properties. So we consider a periodic domain. So periodic domain, you already did that homework assignment, and you have some idea in the previous homework what periodic domain means. So periodic domain, basically, you can visualize it as a circle, and if you have grid here, so this is indices 1, 2, 3, so on, and this is index n minus 1. So that periodic domain, basically there is no boundary, so value of some value for function phi in 1 equals to phi, say n plus 1. So n plus 1 is a ghost point. So basically, basically this is what periodic domain is. And so let's, one of the properties of periodic domain, if you summarize, like you use, we will use it further, if you have some sum over index k of some function or some grid defined function phi, then it is true that if you just, it's the same thing as you have if you added 1 to index, or you subtracted 1 to index, or 2 to index. What is actually changing is just we won't specify them, but what is changing is the summation bounds, but it does not, obviously does not affect the sum, because the sum is determined just by number of grid points. So if you sum them starting from 1, it's the same sum if you start from, say, this point and then you sum these values. So you see that for periodic domain summation, adding some constant integer number to the index does not change the result, and we will use that in our assessment of conservation properties of the scheme. So first of all, does the scheme, does this Berger equation conserve momentum? Yes, it does, because you can rewrite it as the following term in a so-called, so this is advective form, so you have this advective term. But you can write it as in the flux form. For that, you basically just put this u inside of this derivative here. So you can write the same equation and rewrite it in the following term, in the following form. So obviously, these two equations are equivalent; they're the same. In that case, you see you have this. If you now integrate over the whole domain, which is in this case is also periodical, then obviously, well, ddt can be taken out of integral sign, because time is not function of distance. So you have ddt integral from 0 to L. L is the longest distance of u dx. So this is this term, plus 1/2 integral from 0 to L du square dx equals to 0. Now integral of a derivative of a function equal just to that function, so integral of df dx, or df dx like that, dx equals to 0 and L f at L minus F at 0, obviously. So for periodical domain now, so this term equals 1/2 u squared at L minus u squared at 0. And obviously because of periodical domain, those two equal to each other, so this equals to 0. From which it follows conservation of total momentum or integral of u over the whole domain. So we have d dt of that total momentum equals to 0. So this equation preserves total momentum. Now, does it preserve energy? And energy here will define just square. So energy, or kinetic energy, is equals to u squared over 2. So if we now multiply this equation by u, we have d dt u squared over 2 plus, so multiply u squared, and then so taking inside of this we have d dx u cube equals to 0. So what we did, we just multiplied by u and then I take it inside the derivative. And if you now integrate, it's the same thing. It's similar to what we had for momentum. So the integral from 0 to L of u squared over 2 dx equals to 0, because this has similar form to this. It just instead of u squared you have u cube, but it's in a so-called flux form. So it's this formula d dx, and there is no only constant coefficient, is called flux form. And flux form is nice to analyze conservation, because integral of derivative is, as I say, is here is very easy to take. So integral of derivative is just equal to this values of function at the bounds, and in periodical domain it's always 0. So this is similar thing. So we see that that kinetic energy is also conserved. So we have two conservation laws associated with this equation. It conserves momentum and it conserves kinetic energy. So now let's see if our finite difference approximation have similar properties. So now let's try so let's approximate only space derivative. Time derivative, we'll have it analytical. So we have some grid and index k. So now we have duk dt plus uk, and here we will have center differences for space derivative. So this is our approximation to Berger's equation, and see if it conserves momentum. For that, instead of integral, we just use sum over all indexes k. So we have d dt sum of uk plus, here we have 1 over 2 delta x, here we have sum of uk plus 1 minus uk minus 1 equals. So how about this term? Let's only deal with this. Now we can use this property of periodical domain, that summation of if we add 1 or subtract 1 from index, it doesn't really change anything. So what we have here, that if we add 1, we have this guy becomes uk plus 1 uk. And if we look at this, it's the same term as here, so it means that this term, this whole sum will cancel out on periodical domain, and so we have indeed conservation. So this will go to 0, and so we have sum of uk, rate of change in time equal to 0, so sum of uk is conserved, so we indeed have conservation of momentum by using this scheme. Okay, very nice. Now, do we have conservation of kinetic energy? So for that, we take the scheme and multiply it by uk. So we have d dt uk square over 2 plus uk square uk plus 1 minus uk minus 1 divided by 2 delta x. So now let's sum over all grid points. So we have this sum of kinetic, so this is total kinetic energy. Plus 1 over 2 delta x. Here we have sum. Here you have uk plus 1 minus uk minus 1. Okay, so let's do our trick and add 1. So this becomes uk plus 1, uk plus 1, here's uk. So now we have, we can write this whole term as uk plus 1 times uk plus 1 minus uk with minus sign in it. So this expression in the parent. So is this thing cancel? Can this thing cancel? Obviously it's not. Imagine that you have only one grid point that actually has value in it. And so let's say it's u some, I don't know, in some value 5, and here it's all 0, like, no, let me, so now the question is this can be cancelled? And generally I don't see how it can be cancelled, because this uk plus 1 is not necessarily equal to uk, so this term cannot be 0, and those two can be pretty arbitrary numbers, so there is no way, I don't see how arbitrary velocities here, like let's say you just assign some arbitrary random values, how this expression would cancel. So it's not equal to 0. I mean the sum of this. So the sum of this expression cannot be equal to 0, so there is no conservation of kinetic energy. Alright, let's try another scheme. So no conservation. And why it's important, why it's not good thing that you don't conserve kinetic energy. Conservation of momentum is a good thing, but conservation of momentum, momentum has a sign. So it can be positive momentum, it can be negative momentum. And if you have, if you conserve momentum, let's say the total momentum is 0, it means that half your grid points can be very large momentum and half of the grid points can be very negatively not large momentum. So you have some very large positive numbers and very large negative number. So together they still will be 0, but it doesn't prevent instability from happening, right? So your amplitude can be very large and kind of, because conservation of momentum does not guarantee absence of very large numbers. But if you preserve kinetic energy, that's another, because it's quadratic quantity. So if you initially have some momentum, then the sum of all these values in your grid squared should be equal to initial, and initial is a finite number. So all your values, they cannot be very large numbers because they need to add up to maybe initially not very large number. So that actually, that's one of the things that may starve instability from growing, because there is not enough energy for that. So energy is conserved, and in order for instability to grow, you need more energy. And if your scheme preserves kinetic energy, ain't gonna happen because, well, not enough energy. That's why it's very, to prevent nonlinear instability, but not necessarily to prevent noise. Noise may still happen, like in this Berger equation, but at least the scheme will not blow up. It will create all sorts of noises, but never will blow up if you preserve kinetic energy. And our scheme apparently does not preserve kinetic energy. So okay, let's try directly preserving kinetic energy. Actually, we can do that. Well, no. Let's try another scheme. In this case, let's use a flux form. So we use flux form of Berger equation, and we approximated finite differences using flux form. So it's like this. So yeah. So what we did here, just like before, we wrote it in the flux form first, taking u inside, and then just approximated it with this derivative with finite differences, using centered differences. So now let's see if it's preserved momentum. So d dt, sum of uk, plus 1 for delta x. Here we have sum u k plus 1 uk plus 1 minus uk minus 1 uk minus 1. Now you can add 2 to this, and it will get, so add 2 to indices, you have uk plus 1 uk plus 1. So it looks the same as this term. So this term becomes equal to 0. Not this term, but the sum, of course. So sum equals to 0, so a momentum is indeed preserved. So this scheme preserves, conserves momentum, or total momentum. Okay, that's similar to our previous scheme, but so let's see if it conserves kinetic energy. So we have, we multiply by uk square, by uk. So we have, so we multiply by delta x, and here we have sum. Sum uk plus 1 uk plus 1 minus uk minus 1 uk minus 1. Okay, so now let's add 1 this time to this guy. So this guy becomes uk plus 1 uk. So this whole term can be written as uk plus 1 uk plus 1 minus uk. Well, it's the same story as here. We have the same expression except for this guy here. So here we have 1 over 4 delta x, and there we had 1 over 2 delta x with minus sign in it. So it doesn't conserve. So it doesn't conserve, no conservation. So again we failed, even though our scheme conserves momentum, but there is no conservation of kinetic energy. But now if we look carefully, so we have the same term here, and except for it's just different by a factor of 1 over 2 with negative sign. So if we add this scheme to previous scheme like that one with some weighted such that that these two things would cancel, then now this right hand side or this term, advection term, would cancel, and then we will have conservation of kinetic energy. So what I'm talking about, so you see they only different by this coefficient. So our scheme would look something like that. Actually, so basically we're combining those two together, and this 1 over 3 coefficient should be so that it's kind of, first of all, some kind of weighted average, and also it ensures that these two coefficients, well, combining with this coefficient here, so that these two terms would cancel each other. So this is how our scheme would look like, and it's very easy to check if you do. Well, because of our previous consideration that this scheme would conserve kinetic energy. So this is conserves kinetic energy. So see, we by this artificially designed scheme, we and also it would conserve kinetic energy and momentum. So we designed this scheme that would conserve both. So you see, it's not straightforward to just come up. It's pretty easy to conserve momentum. All you have to do is basically to write your equation in flux form. But it's not very easy to conserve momentum. I mean, conserve kinetic energy. You need to make sure that your scheme does conserve kinetic energy. It's not straightforward. So this is our simple example with Berger's equation. Let's now move to different example. So let's now talk about more realistic example. It's let's consider a fluid in some volume, and let's talk about conservation of some quantity transported by fluid in that in some volume. And general statement of conservation of some quantity transported by liquid or fluid is some quantity phi, that the time derivative of that quantity phi equals to, let's say there are some sources and sinks, so let's call them Q. So if Q equal to 0, then there are no sources and sinks, and the phi is of course conserved along the trajectory. So this statement says that it's conservation of phi along some trajectory in the fluid, so some streamline. So you have streamline and your phi is constant along that streamline. if Q is 0. If Q is not 0, like say if you transport say water vapor and there is condensation, some of water vapor will be removed, and then if it's evaporation, some water vapor will be added. So so again, this view is called Lagrangian view. So it's a view of rate of change of some quantity along the trajectory or along the streamline in the fluid. So let's write this derivative in a different form. So because phi is a function of x, y, z, and time, so it's a function of several variables, its differential can be written as the following. This is a basic calculus of multivariate calculus. So these partial derivatives, of course, you know, they taking when you freeze other variables. So for example, partial derivative with respect to time in this case means that it's in a point with fixed x, y, and z coordinates. Partial derivative in this partial derivative in x, it's when you froze time, y, and z. So now if we divide it by dt, by the differential dt, so this will go. And then you have these derivatives with respect to time. And of course, rate of change of x with respect to time is called velocity, which is this case is velocity along the x direction, it's velocity along y direction, and this is velocity along z direction. So we can write then that our equation becomes d phi dt plus u d phi dx plus v d phi dy plus w d phi dz equals to q. So this view is called Eulerian view. So it's definitely different than Lagrangian view, although they of course equivalent. But from our like, what's the difference between them? Lagrangian view says that you are sitting, say, in some boat along this, and you move together with the flow. Let's say that your boat doesn't have any inertia, and you follow your quantity phi. And as you follow it, like let's say that if there are no sources and sinks, this is this time, this is phi, you measure it, you will see that it's constant. So from your point of view, phi does not change along that trajectory. So this is Lagrangian view. And from point of view, from Eulerian point of view, you actually sitting somewhere here, and you don't move anywhere, and you measure this quantity phi, and of course could be some sources and sinks upstream from that point, so your phi will fluctuate, and so you may see something like, you know, some fluctuation of phi. So the same field would be viewed differently in Lagrangian point of view and from Eulerian point of view. And of course, if you have grid, this is it is not very clear how you would use Lagrangian point of view, because it constantly kind of you move along that unpredictable or kind of trajectory which is actually changing with time, and it's if you put your grid points along the trajectory, it actually may change at the next time, so your grid would have to be constantly moved. So generally your grid is fixed. So for you, Eulerian view is the way to go if you use some discrete grid. So we, usually in models, this is what we use. Although we will talk about Lagrangian methods to compute advection even using grid, so-called semi-Lagrangian method. But for now, let's not talk about that. We talk about this Eulerian view. So this statement is kind of can be written a little bit shorter using vector notations. We introduce operator del, derivative operator. It's a vector with components ddx, ddy, ddz, and then vector u equals with components u, v, w. Then these three terms together look like a dot product of two vectors. So this can be written as the following form: u dot gradient of phi. So gradient of phi is a vector, and phi is a scale, that's why it's gradient, and this is dot product between two vectors equals q. So this is much easier much shorter notation. So now, what's our conservation properties that associated with this simple advection or transport equation? We can't really. It's difficult to assess this conservation from Lagrangian point of view, because all you can say that some quantity is conserved along the trajectory, but it doesn't mean that it's not obvious, at least, that if you have some volume, that quantity is actually preserved over total quantity preserved over the given volume. So you have a tank, water tank, and you have some concentration of some scalar there, and it's transported around, and along each trajectory it may be constant, but how can you tell that the total integral of that quantity? Of course it should be, if there are no sinks and sources, it should be conserved in that tank. So at least it's not clear from this equation. So we need to use Euler view for that. For that we would need one more equation, which is called continuity equation, because fluid, the trajectories are not arbitrary. They're such that mass is preserved. So if you just, for example, two trajectories in fluid cannot intersect, so fluid does not move like that. So you always so there should be some continuity. We assume that there is continuity. We're not supersonic fluid here. Consider not supersonic fluid here. So and that is given by continuity equation, which is written using density. So density of fluid plus that product of del with flux of mass equals to 0. So this is continuity equation. I'm not of course, I was not going to derive it. It's very easy to derive, but I think that you derive that equation in one of your dynamics classes. So basically it's a statement of conservation of mass. So how we tell that mass is preserved? Like, let's say that we have our periodical domain, and we integrate over that whole periodical domain. So periodical domain we have d dt, this triple integral over x, y, z of rho dx dy dz plus triple integral of divergence of our flux equals to 0. So this this thing is just summation of d dx rho u d dy rho v and so on. So this integral it's generally like it's a sum of three integrals, one in x direction, one in y direction, one in z direction. And like we did before with this integral differential, those integral will vanish in each of the directions. So this integral is 0. From which you see that integral of density over volume, which is mass, total mass, so total mass does not change. So basically this equation enforces conservation of total mass. So now let's derive conservation of from this. You cannot like just take triple integral here, because it's not clear what's integral of this guy is, because this doesn't look like divergence form. So in order to see some conservation properties, we need to modify this advective term. So this is advection form. We need to convert it into flux form, so-called flux form, or divergence of a flux. So this is flux here, so it should be some divergence of flux of quantity phi. So let's for that let's write it as the following. So we have this equation d phi dt plus, now write it as we want. So we take our u inside, and we also multiply by rho, by density. So what we'll then have, that we have divergence of rho phi u. So this is vector, this is total flux, this is flux of quantity phi. And but we need to, of course, we cannot just arbitrarily put something inside derivative. We need to subtract something out. So we need to subtract this guy, rho phi. Hold on. So we put rho u inside. So now we have phi. Here it's rho u. So we had rho u, and we took rho u inside this del. So we need to now subtract phi del of rho u using chain rule. So it's equals to q. So far we just didn't q times rho, of course. So now we replace this term with the rho dt using continuity equation. So we have rho d phi dt plus del rho phi u, and this one we replace with this guy. So we have plus phi d rho dt equals to q times rho. So now rho d phi dt plus phi d rho dt just combined in one term, which is d dt rho phi plus del rho phi u equals to rho q. So we now rewrote our equation like this into this form. So this one is called flux form. So these two equations are equivalent because of continuity equation. So these two equations now become equivalent to these two equations, written in a flux form. And why flux form is nice? Because now it looks like continuity equation, you see. Instead of rho, you have rho phi. So using the same arguments that we used before, for volume integral over the whole domain, if it's like periodical domain, no flux at the boundaries. So there are no boundaries in the periodical domain. So for periodical domain, the total integral of rho phi should be equal to total integral of sinks and sources. And this term will cancel out. So total integral rate of change of rho phi dx dy dz equals to total integral of all sources and sinks. So this is conservation of mass or conservation of phi. But you see, you need to multiply it by density in order to this flux form to work. So it's not, sometimes people don't realize this thing is not the same thing as d rho phi dt. This is not d rho phi dt. So this equation obtained from this by multiplying by rho, but it's not the same thing. So sometimes I see it actually in papers notation like this, which is wrong. Okay, so now we have flux form of equations, and flux form of equations are very nice to work with, because now we have immediately way to conserve our quantity on a grid. All we have to do is to use flux form of our equation and use finite differences for the flux form. And that way we just basically, like in our previous example of Berger equation, we can easily cancel those terms associated with this divergence and preserve our total quantity that we want to preserve.